All right. And so basically, I'm going to take you through our privacy preserving semantic data warehouse for decentralized drone swarms. Okay. So we are simulating DAVAP, telemetry, and federated aggregation via mobile edge agents. And DAVAP is the protocol we are building for our Pioneer project. And these are my group mates. Yeah, those are our keywords. So the background and introduction. This here is so modern decentralized warfare rely heavily on autonomous drones. That is true. You can see that in Ukraine and Russia. And swarms are vulnerable to radio interference and acoustic command spoofing. So cryptographic frameworks like the DAVAP provide multi-factor physical layer security. However, governing the massive data that streams generated by these swarms presents an infrastructure challenge. So we are introducing our solution is more of a semantic layer that's supposed to bridge the data warehouse with business intelligence. Business intelligence is how do we make sense out of that data? And then the cloud data warehouse is where the data is actually stored. So we have components such as it should be self-service, that means it should be accessible to those who need it and they should access it themselves. It should be scalable, power and speed, and then also flexibility. So traditional relational databases are not capable of handling the chaotic telemetry of edge devices operating in combat zone. So our semantic data warehouse is supposed to bridge this gap and come up with a data warehouse or infrastructure that solves this problem. Yeah. So these are some of the variables our architecture will track: granular agent telemetry, the node uptime, downtime durations, and participation rates. Yeah, so maybe just to add, in a hostile environment, no system is 100% secure. Okay, there will always be a vulnerability. So we are embedding differential privacy just in case someone manages to get into the system. Okay, they will be able to. In case they get in, they will just find calibrated noise. Okay, noise that they won't be able to make sense out of. Yeah, so that will help us hide the data. Yeah, so our architecture guarantees that adversaries cannot reverse engineer and get crucial data just by accessing the system. Okay, so we have our ontology-driven knowledge graph, which acts as an epistemic control plane for the entire operation. So this graph-based infrastructure maps 3 integrated domains. They are the agent nodes, telemetry nodes, and the consensus nodes. Now the agent nodes are the ones that you see here, the ones that are blue, red, and yellow. Those are the agent nodes, which are more like the drones. Okay. Now, amongst those drones, we have telemetry nodes. These are the ones that aggregate the data, and then these are the ones that send the data to the warehouse. Okay. And then the consensus edges are the ones which provide links necessary to verify command execution. So this is normally without quorum while we carry out the majority voting. We use the consensus edges for these command executions. So the related works that have been done in this area, we have AcousticVision Pro, which is an open source platform for room impulse response analysis and acoustic characterization. Okay, so it's an open source tool, but a paper was also published about it. So it uses acoustic fingerprints to verify recording environments and detect mismatches from expected baseline profiles. Yeah, so there is also spectrostability, which is used to detect frequency imbalances or clipping artifacts in propagated audio. And some of the metrics they use to accomplish all this is signal-to-noise ratio, which quantifies speech quality preservation for content-specific evaluation. And then another paper we reviewed was the potential of swarm intelligence in big data analytics. So the paper describes how swarm agents can be used in big data analytics without having to use a central server to analyze the data. So here at each node, you have to extract the features, then you analyze those features, and then you have to deal with variations in case there are multiple of those, okay? And how they deal with this is through the concept called majority voting. So we have borrowed this concept into our project, as I explained earlier. Yeah, then the data can be sent to the server. Then we also have the deployment of an IoT system for adaptive in situ soundscape augmentation. So the paper presents the design and deployment of an IoT-enabled system that uses cloud-based deep learning to perform real-time noise optimization in real-world environments. So this uses both objective acoustic metrics and perceptual context awareness to optimize noise handling to ensure that audio is validated against its expected environment before pattern analysis begins in DFAB. Yeah, so they also use the concept of masking profiles and gain levels to prevent audio degradation as it propagates between swarm agents. And then another related work is a decentralized retrieval augmented generation system with source reliability secured on the blockchain. So this paper illustrates a DRAG system, that's a decentralized retrieval augmented generation system that secures source reliability and update integrity using blockchain-based smart contracts and cryptographic consensus mechanisms. So here, how we would use this in our project, we would have all the data. Once all the data reaches our data warehouse, we then would have to create a vector database such that if someone wanted to query the data, they would just, use text. They would just text and know which nodes are up, which nodes were up between this time and this time. Yeah, that would be it. Yeah. With this method, the DRAG would actually be suitable for people who aren't technical, very technical people, like people who aren't so technical. They wouldn't want to work with commands and terminals and all that. So you just give them a decentralized RAG where they can just type their queries and they get the data. So the next stage is the next paper. The next related work is low Paxos. That's a state machine replication for low resource settings. So the paper introduces an adaptation of the Paxos consensus protocol that's specifically engineered for the unique constraints of low resource and challenged environments. Of course, the assumption, which happens to be true, is that network stability is rarely present in developing world settings. Things such as power outages, unstable network performance, and varying hardware are common. So this protocol, low Paxos, utilizes a profile-driven election mechanism that calculates a replica strength based on the link capacity, latency, packet loss, and process power to designate the most capable leader. Yeah. So for this one, you have swarms. Okay, you have swarms, but then you have a swarm, but then you use all these metrics that have been described here to determine who is going to be the leader in that swarm. So if everyone has data, they all send it to the leader, and then the leader will be the one to communicate with the server. We haven't adopted that in our project because that's dangerous. Yeah, we are trying to avoid single point of failure issues. Yeah, so we come to our problem statement. Our domain application of this one, modern distributed systems rely on multiple heterogeneous data sources, Heterogeneous data sources is data that has been collected from different places. You can have swarm data from Ukraine. You might have swarm data from Russia. You might have some from the US. You might have some from here in Africa. But then when you get it to the central location, that's the warehouse, you just mix it up. Okay. Now that contaminates the data. Okay. So data is supposed to be isolated and managed separately, so that in case there is any issue with a particular set of data that was collected in one area, you can be able to detect that and rectify it. Yeah. So using my example again, if you have data from Russia, Ukraine, you have that separately. You have data from Iran, Israel, you have that data separately, and then you analyze it, okay, independently. Then our computational problem, we are using our DAVAP protocol for decentralized swarm control. And then we have to find a way of preserving privacy in our semantic knowledge graph. Instead of using relational databases, we use the differential privacy for that, as I said earlier. And then use of mobile phones as distributed sensing and processing network. And then unified integration of multiple data sources. Then web-based real-time monitoring and visualization. So our research questions, I won't dwell on these for so long. I'll skip to the methodology. So for our methodology, and let me remove this, put it down here. Our methodology and system architecture. This is our decentralized swarm. It has been deployed in the field. Then this is our data warehouse. Okay, so all these activities are happening in the data warehouse. We have the minimal supervision of acoustic logs. Here, we are reviewing the logs to see the state of each agent or node. And the state tracking and anomaly detection, that is done using the features that have been collected from each agent, and then multivariant time series data. The data is in form of time series because we want to know what's happening and when it happened. The when is very important. So the time series component is what we have to work with here. And then federated aggregation, then differential privacy. As I explained earlier, we have to add some noise using differential privacy. And then also the graph-based aggregation. This is where we get all the data from the nodes and we organize it at the central warehouse. Yeah. So our system architecture, this is how our pipeline works, okay? So at the edge, we have extraction and privacy injection using a technique called local differential privacy. We get the acoustic metrics and the data, we add some noise to it. Yeah, and then from that, we are able to determine the state of a particular agent. That's the uptime and the downtime. And then we use the semantic consensus aggregation. Here, after all the data has been verified and we have confirmed that the agent hasn't been attacked or compromised, we can then add its transactions to the blockchain. Yeah. And that will continue like that. That's the concept of federated consensus, where all the agents carry out a majority voting to achieve that. Yeah, we have some data as well. The data was synthetically generated. Okay, so here we have two classes, class 0 and class 1. Class 0 is the secure agents. Class 1 are the insecure ones. Yeah, and this data set is mainly composed of acoustic sensor features, swarm telemetry features, and consensus metadata showing the agent participation. Yeah, initially in our dashboard, we showed you we had 3 types of agents. There was the secure one, the suspicious one, and the highly risky one. Okay, so highly risky and suspicious have been combined into one class, which is class 1, and then secure is class 0. That's how we are differentiating it. And then we also did a feature correlation map where we wanted to see how each of the features affect each other. So for example, here, you can see that the battery of the node does not affect the signal strength at all. Okay, so here we have all the features and we are looking at how they relate with each other. Now here you can see the latency and the label really do matter. Yeah, they really affect each other. That's about 60%. That's really high. And then we also went ahead to look at principal component analysis, where we wanted to reduce the dimensionality of the feature space so that we can only maintain features that affect the result or the end goal. So from here, we did distinct clusters, suggesting that an ML model can differentiate between benign and spoofed. Yeah. So the model selection, we trained models to detect anomalies based on spoofing attempts, and the baseline models we used were the logistic regression, the random forest, and the MLP. So that particularly helped us understand how the known models behave. So when we brought in our federated graph neural network as our proposed solution, this allows models to be trained locally, and only model updates are aggregated. So we do some bit of federated learning, minimizes data exposure by keeping the local data on the devices. And that's well illustrated by this diagram. We have a central server, which has a global model with global weights, So every time this model is updated or retrained, the weights on the central server are modified. Okay. Then from there, the global model is sent to each of the clients. Those are the agents. We share the model weights to each of the agents, and then these agents will go ahead and update the weights of the local model. It can be through, they go ahead to update the weights of the local model, and then the local models also learn from their own mistakes. Okay, here we have local graph data. We extract the features from the node, and then we train the local model based on that. Yeah, so when we did our sample training, we had some output results. And as you see here, we have our logistic regression, we had our random forest, and our MLP. All these were trained here, and you can see this. The score was above 80% for accuracy, precision, recall, and F1 score. But when you look at our federated graph neural network, it was just slightly close to 65. Okay, I'm going to tell you why. I'm going to show you why we still had to go with our federated graph neural network. Okay, so as you see here, we have our devices. These are the number of devices we have in the swarm. This is the time it takes to use to get an SQL query using the Galaxy schema, and then the time it takes for our graph to query the same data. So in 0.01 seconds, our SQL query can only pick 18 results. Our graph can pick 29 in a much faster time, in close to 100 times faster. Okay, when we increase to 528, this takes 0.03 0.03 seconds. And then our graph time is even much faster. It picks up 42, the SQL query only picks up 28. When you look at the other results, our graph really performs much, much better than the SQL, than the Galaxy schema. Yeah, so that is basically it, and maybe I can go ahead and show our developed product. This is the local subgraph topology. As you can see, this node has been selected. This node has been selected, and it appears here and shows all the neighbors it's communicating with in the graph. And then we can also look at our acoustic signature analysis. Then we can be able to see the deviation percentage. Of course, 92% is so high. That's why this agent has been flagged as red. Okay. Yeah. So that's basically it. And I'll go to the limitations of that we have faced. One of our limitations are hardware and the acoustic shift. We are using mobile phones, as our title says. That's because we cannot afford drones for now. And then different smartphone models possess different microphone frequency responses and internal noise cancellation algorithms. Yep. When someone has the Techno and someone else has an iPhone XR, another one has an iPhone 17, another one has that's a problem. That's a problem when it comes to adding noise to the data and then de-encrypting that noise again at the receiving end. Yeah, and then with local differential privacy at high privacy thresholds, the injected noise degrades the acoustic feature vectors, leading to false negative threats. Yeah, in limited scenarios of severe network jamming, where over 60% of the swarm experiences simultaneous downtime, the resulting noise graph becomes extremely sparse. So our conclusion, our architecture successfully harmonizes dynamic agent telemetry, such as uptime and downtime. Our architecture ensures blockchain consensus participation with differentially private acoustic signatures, and then it also ensures that military commanders act only on cryptographically verified, privacy-compliant evidence. Yeah, so our feature works, we want to deploy quantized lightweight models directly onto edge devices, which are drones. And then we also want to push both semantic extraction and anomaly detection entirely to the offline edge to reduce cloud communication bandwidth. And then we want to transition this validated architecture from mobile phone proxies to the physical hardware. Yeah, that is it from me. These are the references, a few from the related works, and thank you.